Hey, today I'm going to explain the legendary architecture, transformer architecture. I will explain the math, the operation, and how it works. So if you are kind of using language models like BERT, RoBERTa, GPT-3s a lot, and you want to understand how they actually work in a more detailed way, then this video is for you. I'm going to explain the math and more details behind that. And as you may know, in recent years, those language models, pre-trained language models, are very powerful and achieve a lot of state-of-the-art results. And all of those neural network language models are based on transformer architecture. And by the way, if you would like to receive more deep learning videos like this, I release the videos on the weekly basis. Don't forget to subscribe. And your subscription is really my best encouragement to make more videos like this. And yes, this is the overview of transformer architecture. It consists of one encoder part on the left, so encoder, and it also consists of one, decoder part on the right. This is original architectural design because they first designed this to solve the translation problem. So you will have encoder and a decoder. But definitely for most language models, they only employ the encoder part. But in today's video, I am going to explain these two parts. And in the encoder part, one block consists of two sublayers. One is called attention head, multi-attention head layer. Another is feedforward neural network. And definitely, you can just say one block contains two sublayers. And they use the attention mechanism to make the feedforward neural network be able to model the long-term dependencies. That's really unexpected move because before they released this paper, most people use recurrent neural networks to model long-term dependencies. Many people really think the feedforward neural network will work on language data, which has the sequential nature. So combine the feedforward and the attention mechanism, make attention layer. Now you can model long-term dependencies really well. That's pretty interesting mathematical wise, if you really think about it. And in the attention one, in the one transformer encoder block, there's actually something more complex going on. You will not only have the attention and the feedforward layer, you also have the layer normalization operation after that, and also the addition, basically is a residual connection to allow your models to have the beta connection with your raw input. So you have these layers after feedforward layers and attention layers. In fact, all the sublayers will have this residual connection and layer normalizations after that. So let's look at what the residual connection, which is addition operation, and layer normalization works. So in the residual connection, it's actually very simple. Let's say you have your input X, and you have your sublayer, which we kind of write this as a function here, sublayer function. Then after your sublayer operation, you have your output here. Then your output is Y, temporary output. Then you want to just do the addition for your output and your original input X. Then you have your new output. This is called sublayer residual connection. Basically, is to let your model to have a beta connection with your original input. Then after you do a residual connection, you will have layer normalization to normalize the layer, which is quite common in most of neural network architecture. And the residual connection was first introduced in the computer vision, I believe. It's a neural network architecture called ResNet, which have a lot of residual connection, and it's proven that it's more effective than the neural network have no residual connections. So that's why the transformer architecture added a residual connection to every sublayers. And because you're doing the addition residual connection for your layer output and the original input, right? If you want to do addition, then your dimension must be the same. So that's why they set up the all sublayers dimension, input and dimension to a sublayer, and the output dimension to a sublayer to be the same. And also the embedding layer, the word embedding layers be the same. And all of them are 112 dimension in this paper. And probably let me explain what's embedding layer first. The embedding layer is like a word embedding layer to transfer your token, which is word, token representation to the numerical representation. It's like transfer apple to a vector. Okay, so here is the decoder structure. Decoder is a little bit different from encoder because you need to consider your already decoded output and also the encoder's output, because this is for machine translation, so keep it in mind. And the one decoder block actually consists of 3 components. 2 of them are the same as the encoder attention layer and the feedforward layer. And they also have the third one. The third is the extra one, which is mask multi-head attention. The mask multi-head attention is basically they block certain information from the future. When you do the machine translation in the decoding part, you predict your the sentence in your target languages, 1 token by 1 token. Then, because of the nature of transformer architecture, sometimes you will accidentally access the information from the future, from the right part of the sentence. There is a way to block that. So let's take a machine translation as example. And transformer model actually trying to mimic the behavior of sequence-to-sequence model. So let's just look at translation in the sequence-to-sequence model point of view. So let's say we are doing a translation from English to French. The source sentence is, I have a pen, and we want to translate it to the French equivalent. Then, because the sequence-to-sequence model actually does this sequentially, you will predict the first token, your input, I have a pen, then you will predict what is supposed to be the first token in this target sentence, jar, right? And you also, after you predict the jar, you will predict the next token, UN. I don't know how to pronounce it, sorry. And let's say after these 2 steps, then the transformer wants to predict the sequence-to-sequence models, wants to predict the next token, basically the last token of the target sentence. Then before that, you will need to calculate the representation of this first token and also the second token. And when it tries to calculate the first token's representation, if we don't mask it, then because of the structure of transformer, you will be able to access the information from the token number 2, but it's not allowed in sequence-to-sequence architecture because this consider the future information. We don't want the model to know that when you calculate representation of it, because the traditional sequence-to-sequence model just doesn't do that. That's why the paper wants to make it looks like, at least behavior like a sequence-to-sequence model. So you want to mask this one. And just like I said, when you process these tokens, you calculate the representation of this token. Then you want to block the information from the future token, which is this. Then after that, you will have the representation of this. And when you process this token, then you can actually access the information of here. So they will block the information after yourself, and you will have the access to the information up to yourself. So this is time step 0, time step 1. If you are processing this token, you will have the information like at least from 0 to 1. Okay, so this is the high level of how and why they want to use the mask attention thing, basically to mimic the sequence-to-sequence model. So yeah, this is what we are talking about, this layer. Okay. So because we just mentioned the attention a little bit, right? So let's talk about attention. What does attention mean here? Attention mechanism, and here is like attention layer. Okay, so if we really want to understand the concept of attention, let's probably just start it from the visual thing. That's easier. So if I ask you how many rivers are there, you'll probably focus, when I ask you this question, you'll probably immediately focus on those areas that have reflection, because it's highly likely to be water, right? So you'll focus on the area that I circle, which is the area in the circle, ray circle. Then what if I ask you another question? How many humans are there? Then you'll probably focus on other area, which can be this area, these areas. So you will focus on this, like the area they have probably like the human shape. Also this one is also probably human, right? Then what if I ask you how many rivers are there? Oh, sorry. What if I ask you another question? How many roads are there? And you will probably focus on these things. Looks like a road, and it's like a long shape, narrow bend, and without too much reflection of the light. Then it will be probably very likely to be roads. So your visual cue actually change depending on my questions to you. So you can actually see my questions as a query, and the location you focus on in this picture, it's key, and the value is the corresponding RGB value for this position. So if you look at this pixel 1, pixel 2, if I ask you how many rows are there, you will focus on this kind of these pixels. Then the value of them is value. So we can roughly visualize the attention, or at least summarize attention mechanism in this way. This is also the very main contribution of this paper. Attention is all you need. They kind of formalize the attention a little bit more, because before this there are so many different ways of doing attentions. In this paper, they further like formalize the attention mechanism. So the query is the question I ask you, right? Then you will have the key and the value pairs. In the previous example, the key is the location of pixel, and the value is RGB. In language context, they will be different, and depending on what kind of attention application you're using. If it's a self attention, then you'll have yourself as query, yourself as key, yourself as value, which I will cover later. So there was a very popular attention. It's called dot product attention, and in this paper they modify this as a scale dot product attention. So it's basically when you have the key, you have value, and what the model is doing is it calculates the compatibility between query and the key. If they are very compatible, then their dot product will be close to 1. If they are not really compatible, then the dot product will be close to 0. And if they are compatible, then they have the high value of dot product. Then which means their value, the value corresponding to this key and the query, will have a high importance. If they are not really compatible, then the value assigned to the importance of assigned to this value then will be very low. Okay, so let's formalize this a little bit more. Scale dot product attention. Basically, you can see this as a attention query, key, and value, and you do a dot product between a query and the key here. Then you do a scale. You kind of normalize it a little bit, because if you have a very high dimensional query and the key, then your variation of dot product of this will be higher. Then they found out if you kind of scaled it back by the dimension of key, they will have a better result. And you will have the value here for every, because this Q is actually a matrix, this K is also a matrix. So you have the matrix of dot product, because you kind of do the dot product operation between matrix. Then you will have the result of this dot product. And you do a softmax, basically to normalize this from 0 to 1, from 0 to 1, every element, and the summation of them is 1. Then you do the multiplication to this attention matrix, which is your result, to your value matrix. Then you have the importance to each element in this value matrix. Okay. To illustrate key value query attention relation further, let's take a self-attention as an example, because it's a very important component in transformer architecture. So there are two kind of self-attentions here. One is encoder self-attention, that's here, encoder self-attention. Another is decoder self-attention. But basically they are very similar. It's to use yourself, which is your, you can see in the encoder self-attention, your input sequence as key, at the same time as value, and also as query. So I will take this as an example. Let's say we have the input, I have a pen. Then you need to calculate the key value capacity, right? So it's, no, sorry. You need to calculate the key and the query capacity. And your key and query all are yourself. So it's all this sequence, I have a pen. Then you will need to do the dot product. And after the dot product, you will have the attention matrix, or you can say this as attention map, which tells you when you process certain token I, how much attention you need to pay to token I or token have, token pen. Then you will have this 4 times 4 matrix, depends on how many tokens you have. If you have L tokens, you have L times L matrix. And all value in this dimension will, if you sum all them up, they will be equals to 1, because you do a softmax. And after that, you can know how much weight you need to put. For example, when the model processes the token I, it actually, this is just that I made up those values by myself to illustrate. But in the reality, it's very similar. You in the I, when you process the model process the token I, it pays extra attention to the token half. So token half will have its representation vector here. Then you will have the better weight to this representation vector. And also same goes to other token. When you process the half, the token half, then the model pays more attention to the token I. Yeah. and the sum out, if you sum out all of them in this axis, they will be just equals to 1. And same goes to other things. So it basically is to tell the model what tokens are important when you process a given token. And you will have the different weight to their vectors. Then you aggregate them, maybe do the addition, or you can actually do other operation. Okay, so that's a scale dot product attention. But the story is not just that. In the transformer architecture, they found out if you just input key value query, you just do that. You don't have any like learn parameters there, and the result will not be the ideal. So that's why they put a learn projection layer here, a learn matrix here between key query and the value. So originally you have a key, then you will do the matrix multiplication to the weight matrix for key, then you will have your real key value here. And also same goes to the query. You also will have a query matrix, and after that you will have the real query matrix value as well. And that's just how they improve the model, because your attention mechanism can learn something depending on the task. This metric can be changed. And also the trick is they actually use this as a dimension reduction, so that they can put more attention heads, which I'll cover later. It's here. In their implementation, they have 8 attention heads. So you will have 8 different weight matrix here, 8 different weight matrix here in each layer. Then after that, you reduce that to lower dimension. In this case, because they have 8 different attention matrix here. So original their dimensions input is 1 to 1/12, and if you divide 1/12 by 8, how many do you have? You have 64. So after this weight matrix, you will have a lower dimension vectors, list of vectors here, 64 dimension list of vectors, 64. Then you have 8 of them for each token. So for the token, maybe I have a pen. For token I, you have 64 dimensions. After this operation, this key query operation, everything. Then how do you sum that up? So let's look at the life cycle of the value vector. Probably can make you understand it better. Okay, so originally we will have an input, which is token, right? Token, input token. I have a pen. Every word is a token. Then after word embedding, you have be able to convert this token to 112 dimensional embedding belong to this token. And then you will have an attention layer. And attention layer here is not a single layer. You actually have 8 different layers in this transformer architecture. Or you can call it 8 different attention heads. I will call it attention heads instead. Okay, so you have attention heads. Then every attention head will have one learn projection layer, which will reduce your dimension from 112 to 64. Then you will have because they will have 8 attention heads, so you have 8 64 dimensional vectors. Then after attention layer, you will do one operation, which is concatenation. You concatenate all these 8 vectors into one. So you will have 64 times a dimension, which is 1/12. So you come back to 1/12 dimension after one attention layer. So the life cycle is like input is 112 vector, 112 dimensional vector, and the output is still 112 dimensional vector. But in the middle of the layer, you actually decompose it to 64 dimensional things and recombine it. Okay, so yeah, that's just how it looks like. And definitely this, I'm just saying for the value matrix. Then you have the key matrix, you have the query, but in the self-attention layer, all of them are the same thing. I mean, the very similar. It's not exactly the same. Okay, so yeah, this is just the scaled dot product attention and the multi-head attention. So key, query, compatibility, then you have attention matrix, and you apply this attention matrix to your value matrix. And in this case, is number of your token times of number of your token. And every matrix, every element in this matrix is a vector. Okay, so I hope it's like a little bit clear now. Definitely, it's not a one-time thing. You need to go through the paper. You need to go through this video maybe for multiple times in order to understand it better. It's really probably hard to just understand it just by reading the paper or watching this video once. Okay, so this is a better illustration of the multi-head attention. You have key, you have value, you have key, you have query. Okay, then you have the linear projection layer, which you have added in this architecture, in this paper's specific transformer architecture. Definitely your head is H. You can change it to whatever numbers you like. Okay, so you have a linear projection layers. Then you have the scale dot product attention, which will have 8 of them, number of 8, H, and you concatenate back to the original dimension. It's like your input dimension. Okay, then that's another projection layer. It's just the projection layer. Then after that, you have your output. So how to interpret this? Your input of embeddings and output of embedding are exactly the same shape, but in the middle of this layer, you actually aggregate the information among tokens. I have a pen, it's a your input. I have a pen. Then in the attention, you actually aggregate the information between tokens. Then you have the output here. Still, you will still have the 4 vectors for each position. I have a pen, but the vector for, let's say, first token I is not just from the token I. You actually aggregate the information from other token. Have a pen. This is how the attention works, or you can at least you can interpret it in this way. Okay, so there are a 3 different types of application of attention in transform architecture. The first one is encoder and decoder attention, which is you have the query from decoder layer, from your decoder layer, your query, and your key is from your encoder layer output, and your value is also from your encoder layer output. So how you select the importance of your value is depending on your compatibility between decoder output and the encoder output. Okay, so this is trying to mimic the sequence-to-sequence model. So probably let's take a look at from this big picture. Okay, so the decoder encoder layers here. So as you can see, you will have the query from your decoder output here, decoder output here. Then you will have your key and the value from your encoder output here. So your key and the value is from your encoder, which means you want to pay different attention to your input token. I have a pen. You want the goal is you translate this to French sentence, French equivalence, and depending on how you already translate, Joe and something, you already translate this. You will focus on different thing because you already know this is equals to I have. Then you want to translate this as last token is actually pen, right? Stilo. Then how would you want to focus? If you are the human, you will want to focus on the token pen, right? So this is like how it works. Your query is this, and your key is this, your value is this. Depending on different query, you will want to focus on different thing. In this, at least for this query, you will want to focus on the pen more. A model will also do the same thing. This is what model will end up learning. Okay, so high level is this. Okay, and for the encoder self-attention is easy. Query, key, and value all are from the same place, which is previous encoder output. And the decoder self-attention also very straightforward. Key, query, and the value all are from the previous decoder output. But just then you need to keep one thing in mind. It does a masking to prevent the model have access to the future information. So if you remember this picture, basically when we translate this, right, when we want to predict the token, this stilo, sorry, I don't know how to pronounce French, and you will have these two token, June and you need to calculate the representation of them. And when you calculate the representation of the first token, you cannot let the model to have the access to the second token. This is just what I mean by masking. So that's the only difference between decoder self-attention and the encoder self-attention. You need masking. And let's just take a look at the encoder self-attention, because this is very common in the language models like BERT, GPT-3. When the model is processing token, it's actually processing token one by one, and definitely it's happening in a parallel manner. But it just process one operation is to process one token. So when the model is process the token making, you will have the different attention to these the tokens in this input sequence, which is also itself, right? If you take a look, they are actually the same sequence, but the model will have different focuses on different tokens. And in this case, in this attention head, model focus on more difficult, these two tokens. And in different attention heads, they will have different attention patterns. This is very interesting. And in the BERT architecture, let's just take the BERT as example. The BERT-based model, you have 12 attention heads each layer, and you have 12 layers. So you will have 12 times 12, which is 144 attention maps or attention matrix for one input. Okay, so now we also want to understand what does the feedforward neural network mean, because after the attention layer, you will have another sub-layer, which is feedforward layer, and it's position-wise. And in this feedforward layer, it's quite straightforward. It has two projection layers. It's actually two layers, but it's one feedforward neural network here. Consists of two layers. So it's just after one layer here, then you will have the non-linearity to select the max between 0 and your value. And then you have a bias term here. So it's quite straightforward. and they apply this feedforward layer to each position separately, identically. So this for different tokens, like you have pen, I have a pen as input. You apply the same feedforward layer to each of them. So for different token, you still use the same matrix, same feedforward matrix here, and the bias matrix as well. So that's the beauty of transformer. They use one feedforward layer to apply to the token that happen in a different time step, which means in the different position. Because we already have the attention layer here, so it actually dares to model the long-term dependencies. And not to mention, we also have the positional encoding before that, which I will cover later. So because you have actually two layers here, right? Fully connection layers. One is W1 and another is W2. And we call this W1 the inner layer. In the transformer architecture, the inner layer have higher dimension than input and output layer. Inner layer have 2048 dimensions, so it basically upsize your vectors to higher dimension. And you have the output layers, which is another fully connected layers, to reduce your dimension to 112. So your input and output, the dimension will be still the same. Input equals output, which is 112. But in the middle of layer, you actually increase the dimension a bit. Then let's talk about the word embedding. In the transformer architecture, you first have the word embedding. Then you have your transformer block, right? So the word embedding is actually important. The word embedding is very important. It process your input. Your input is just a token, which will be represented in a 1-hot encoding. If you don't know 1-hot encoding, you can Google that a bit and look at the Wikipedia's data. Then you probably can have a certain sense of it. Then your 1-hot encoding is just the way to normally in NLP we use to represent the word, the vocabulary. Then you will have your word embedding. It's a very simple feedforward neural network with a softmax of layers. It's not if with softmax to normalize that a bit. Then you will have the vectors as output. In this case, you will have 512 dimensional vectors, which is already normalized by the softmax layer. Okay, so this is a word embedding. The meaning is convert the tokens to numerical vector, and it's totally learn layer. In transformer, you will have a learn matrix in this layer. Okay, so they also have another use case, which is in the output, final output. In the decoder output, it actually is a vector, 512 dimensional vector. Then you will put this vector to the feedforward layer, and it will actually does the opposite. It converts your vector, numerical vector, to 1-hot encoding, so that you can know what your output actually is. Your original, you have the vector, then you convert to a token. Let's say maybe you are doing the decoding, you're doing the translation from French to English. Then you will have you already have I have, and you want I have a. Then you are doing this prediction. What's the next token? Then you have the vector, one vector here. Then you need to put this vector to embedding layer, reverse embedding layer. Then you will convert it to it actually tells you that's actually the last token should be pen. Okay, so in the transformer architecture, this feedforward, this embedding layers is shared in the encoder input and also the final output layers. They just share the same matrix. Same matrix or embedding matrix. Okay, so let's talk about position encoding. It's actually one of the very important part of transformer, because you have input embedding, right? You have embedding layer, which we cover. You convert your token to a vector, numerical vector, and you have a list of tokens, so you have a list of numerical vectors. But how can model know which token comes first, which token comes next? Like model, if you just apply the feedforward neural network separately to them, then the model actually don't know their position, which one is in the position 1, which is position 2. Model does not have any information about that. That's why we need a positional encoding, which encodes the position information. So there are so many different ways to encode the positional information. You can definitely do one very straightforward way. Let's say because you have to generate this positional encoding in the end will be we'll do the addition with your token embeddings. So in order to they then compatible, you need to have 512 dimensional vector for each position. Then the very straightforward way is to just you hard code, and let's say in the position 1, every dimension value in this position 1 is 1. Then you have 112. Every of them is 1. Then you can do another way, and so on. The dimension 2, every element in this vector, dimension 2 vectors, is 2. Then just to the position I, every element in your vector is I. And repeat 112 times. And this is a very straightforward way to do. But the result will definitely not be ideal because a lot of reasons. It's just not a good way to represent those information, and not to mention your vectors is not normalized. Maybe you can try, maybe you can have a good result, but at least according to the prior research, this is not a good way. So what's a good way to represent information, position information? In this paper, they chose to use sine wave to represent the dimension, the even dimension, and the cosine wave to represent the dimension that's in odd number. So for every dimension, you will have a different wavelength. This is control the wavelength, and your position for different position, you will have a different phase in this sine wave. So in the dimension maybe 1, you will have the same wavelength, but in a different position in the dimension 1, you will have a different phase. So what do I mean by this? They say if you fix your dimension, dimension equals 1, for example, then in a different position, you will have a different value that's in your sine wave. So you will really not repeat your value until you run out of a cycle, until you run a cycle. And in the different dimension, your sine wave will have a different wavelength. Then you have in the different position, you have different value, different phase. Okay, so let's just take a look at one very easy example, probably, which is let's fix the position. Let the position equals to 1. Then we can observe what happened in a different dimension. So in the dimension 2, you can write down this formula. Dimension 2, it can be represented by this sine wave. I will be equal to I equals 1 to here. In the dimension 3, you can write this to this cosine wave. And the only difference between these values is one is sine, one is cosine. And in the dimension 4, which I will be equals to 2, then you have this. This is position 1. And the dimension 4 in this position 1 vector. You will have 112, of course. Then dimension 5, I will equal to 5. So you can see in the position 1, your vector element in different dimension will have different value. So that's how it encodes the information. And another way to look at it is we fix the dimension equals to 1. Then we look at the different positions, dimension 1, because you have vector, right? This is dimension 0, dimension 1, and dimension 111 element. And we only look at this element in position maybe 0 to, in position 1 to 3. Okay, in position 1, in the position 1, sorry, I think this is dimension 2. They say it's dimension 2, but that doesn't matter. In position 1, in the fixed dimension, you will have different phase here. This is represent the wavelength, because you fix the dimension, so your wavelength is fixed. Then you only differ in this numerator, which will control your phase of your sine wave. So you have very different sine wave, different phase of sine wave. The value of different phase, depending on your position, you have different value here. This is your sine wave. Okay, so I hope you can get a sense of why they use sine wave to represent the positional encoding. It's just a hard-coded way, but it's better than you directly assign a very pure value to each position. They just use a more sophisticated way to represent that, but it's fixed. If you, no matter what kind of input you have, in the fixed dimension, the fixed position, you have the same value, exactly the same value. So that's how model memorize which position is that. And because of the residual connection, model can have the access to original raw input. So that's why it will not lose the information of position. Okay, so in the implementation, you have like embeddings for your tokens. After your word embedding, every word have one embedding. Then you will do addition. You will sum them up with your position embedding, which is dimensions 112. You just do a summation. Then you have the embeddings with the positional signal, which is here. Then you feed this into your attention transformer block, which contains attention layer and the feedforward layer. So that's how it works. And this paper also want to argue why they chose self-attention. There are a few reasons. First is it just has a lower per layer capacity. If you compare this to recurrent neural network, convolutional neural network, and you also have the higher parallel ability. It's much highly parallelable than recurrent neural network, which I'll cover later. And also the path between dependencies is just shorter, equals to 1. Okay, let's talk about layer capacity. I think it's straightforward. It's you just need to do one attention matrix calculation, then feedforward neural network. Okay, but what does the parallelable means? Because in the recurrent neural network, you need to calculate each token by token. You need to calculate time step 1. I have a pen. As an example, I have a pen. You need to calculate the representation of I first. Then after that, you calculate the representation half. Then you calculate. Basically, you do this time in an autoregressive manner. If you want to calculate pen, you cannot do that before you calculate representation of these 3 tokens. This is just how the recurrent neural network works. It's just a highly constrained to your time capacity will be n to your token. If you have n tokens, you need to have n times more time to calculate this sequence. But in the transformer architecture, because it's actually a feedforward neural network, you will not need to wait for the previous tokens to be calculated. You can just calculate them parallelly because you apply the feedforward network equally to each token. You don't need to wait before the previous token to be calculated. You can just calculate them at the same time. Okay, so this is a layer complexity and also parallelization of the transformer. And also in a recurrent neural network, if you want to model the long-term dependencies, you actually need to, when you do the gradient descent or let's say the bit propagation, if you want to model the relationship, the dependency between I and the pen is actually owned by I, right? Then you will need to do the bit propagation through 3 tokens before in order to understand their relationship. But in this process, you do a lot of bit propagation. Then your gradient will actually sometimes vanish or become too big. So that's a problem with a recurrent neural network. You need to do n time. Let's say you have n tokens. Then the maximum distance among these 2 tokens will be n. Max pass between this long dependency is n. But in a transformer, you can have the attention that directly point this token, the last token, to the first token by using attention matrix. So the maximum distance between them is just 1. No matter how many tokens you have, even you have 1 million tokens, you just need to have 1 distance between them. In the recurrent neural network, will become 1 million. Okay, so this is the capacity part. And let's just look at the table that summarized what I just said. So for the layer capacity, you will have n is the number of your token. N is the number of your tokens. You have n squared because you need to do the matrix, attention matrix, which will be n times n. And this is if your n is you have a lot of n, then your layer capacity will be big. But normally, your n is much smaller than d because d is dimension. Usually you have 112 or like 768. Normally it's like much larger than the number of your token you have. Okay, so in the normal cases, your complexity per layer will be smaller than recurrent neural network, unless you are processing a very, very long document. Then you need a space. You need to have the restricted self-attention, or there's definitely a lot more other solutions. For example, long former if you are interested. Okay, so the sequential operations is what I mean. In the recurrent neural network, you need to, if you have n token, you need to do n times sequential operations. But in the self-attention, you just need to do 1 time. You don't need to wait for anyone. You just do 1 time and calculate them all in parallel. And that's all. Then the maximum path length is basically the long-term dependency path. In self-attention, there's just 1. No matter how long your sequence is, you can just attend to that by attention matrix. But in your recurrent neural network, it's very hard to model that. You need to go through n tokens to get the first token. So it's n. You have really, really long tokens, then your long-term dependency will be really, really hard to model. Okay, so that's another variation. It's a self-attention. Basically, it's if you have the too long sentence sequence, then you need to trunk them out. Then only calculate a sub-attention matrix. So, but I'm not going to cover that too much. So basically, that's it. That's the most details that you have to know in transformer architecture. And definitely, that's a good thing that you can last to this moment. It's quite a long video. So congratulations. I hope you now understand the transformer architectures better, at least before you you watch this video. So yes, and I will definitely release more deep learning related videos like this. So if you like it, please subscribe and you can receive more relevant content. And also it's the best encouragement for me. And yeah, that's all for today. If you like the video, give it a like. And other than that, take care. And I will see you in my next video.